I'd first like to start by thanking Ilya and Andreas for hosting this, and MSA for hosting this, and for everyone for staying so late in the series of talks. I have to say, I really feel for Xiaobin Chao, who's up next. I think the sun just rose in Nanjing, so. So in this presentation, I'll be talking about the generalities of isotope fractionation theory, with a focus on triple oxygen isotope fractionation. The proverbial Mount Fuji in this case is the merging and hopeful matching of theory to experiment. To get there, we need to know two things. What does theory allow, and how precise and accurate is theory? In theoretical studies, the primary limits affordability, so we need to have some idea how accurate affordable theory is for the calculation of isotope effects. In this talk, I'll broadly cover the basics of isotope fractionation theory. Using that framework, we'll discuss the limits of equilibrium isotope effects and briefly touch on kinetic isotope effects. I'll finish this talk with a case study involving the application of affordable theoretical methods to real systems, particularly liquid water and quartz. So why do we need theory? We need theory to evaluate processes that are experimentally intractable. For instance, in sulfide oxidation, there are intermediates that can't easily be pulled out. We also need theory to inform experimental results. And for instance, kinetic isotope effects where calculated effect depends on a non-observable, the transition state. And finally, we need theory to ground experiments in the same way that experiments are needed to ground theory. So in the path at the top, we'll start with molecular motions. Like masses attached to springs, molecules can vibrate. However, because atoms are very light, these vibrations are characterized by a significant quantum mechanical component. In addition to vibrations, molecules can rotate. They can also translate. And these molecular motions for a statistical system of molecules dictate only a portion of the functions describing the free energy of that system. However, the majority of the free energy is governed by interactions with electrons. Conveniently, because isotopes have the same charge, substituting an isotope has a negligible influence on the electrons, meaning we can ignore the largest contribution and reduce the partition functions to just the contributions from molecular motions. The theory of isotope fractionation really got its start with the 1947 release of a pair of papers by Urey and Bigleis and Goport-Mayer. You've heard about these papers already in the talks earlier. The equation they presented amounts to a calculation of the equilibrium constants between the species of interest and a monatomic species with no isotopic preference. This reduced partition function ratio can be thought of as a molecular system's affinity for one isotope over another. The results of this equation has two significant names, RPFR and beta, or specifically beta for the harmonic contribution. The ZPE and EXC terms that are on, the ZPE and EXC terms represent the 0 point, the ground state, and the vibrationally excited states. The MMI term, on the other hand, this covers the contribution from translations and rotations. The MMI terms derive from the product rule, and this rule in essence says, at least for our purposes, that according to classical physics, isotope exchange reactions yield no isotope fractionation. As a result, we can represent the largely classical translational rotational partition function ratio using the inverse of the classical vibrational partition function. This result requires only two inputs. It requires a list of frequencies, 3n minus 6, with n being the number of atoms in that molecule or model, and a temperature. This equation uses several approximations, the most notable of which is the harmonic oscillator approximation. There are corrections for each of these approximations, but they really can, for the most part, be neglected. The exception to that is when we have to consider molecules that contain hydrogen, so such as water, as well as some organic molecules. In modeling extended systems and condensed states, it's important to note that this MMI term approaches the ratio of the isotopic masses to the 3/2 power. This can conceptually be thought of as the mass difference imparted by the substitution of an isotope, say a mass difference change of 2, is negligible for the mass of a very large molecule. So using values derived from that equation, we can then calculate a fractionation factor, alpha, which you've seen many times in the talk so far. This alpha is the ratio of the 18 to 16 ratios for one species relative to another. For instance, for CO2 water equilibrium, alpha between CO2 and water is 1.04 at 25 degrees Celsius, which amounts to a difference in delta 18 of about 41 per mil. So this brings me into the triple oxygen isotope relationships. Substituting a different mass of the same element, a different isotope of the same element, changes molecular vibrations, but in a way that is mass dependent. This leads to a correlation between isotope effects involving different isotopes of the same element. So we describe these correlations using a set of parameters, which I'll briefly go over. There is theta, which is the slope in log alpha space. For instance, at 25 degrees Celsius, the theta for CO2 and water is predicted to be 0.524. But there's also this parameter kappa. And kappa can be thought of as a theta, but specifically between whatever molecule you have of interest, say water, and a monatomic oxygen. So an oxygen that has or a species that has no preference for one isotope over the other. For instance, the kappa for liquid water at 25 degrees Celsius is 0.5305. Values of kappa have a high temperature and a lower limit. That it's a low temperature limit, but it's also a high molecular mass limit. The high temperature limit is 0.5305, which is also the high temperature limit of theta. The lower limit is about 0.523. Now, you can also use another parameter, cap17. So you can measure two species, and those two species would have a difference in cap17, defined by this equation here. So again, using CO2 water as an example, that difference would be about minus 0.24. In this definition, there are different reference lines that can be used. Throughout the talk, 0.528 has largely been used. For the plots that I'm going to show from here, I'm going to be using 0.5305. That is used solely just to make the plots look a little nicer, to make a little bit more sense. Okay. So to approximate the limits of theta for equilibrium exchanges, I can use a Monte Carlo model for random pairs of diatomic molecules. This model, the model parameters for the equations are given here. I can use the previous Bigleisen-Meyer-Urey model and combine that with a range of masses for the secondary mass and bond force constants. These bond force constants vary from the bond force constant of carbon monoxide, a very strong triple bond, to 1/8, which is just a value that's close to a very weak bond. So the model involves randomly varying these variables, calculating frequencies for those molecules, calculating the mass dependency, and then outputting isotope effects. This is the result for that model. On the y-axis, we have theta, and on the x-axis is alpha. Note that these are very large values because some of the model results are things like a triple bonded hydrogen, or they would equate to something like a triple bonded hydrogen being compared to an oxygen atom or something. So there's this feature at alpha equals 1, and that's when we originally did these models, that was the most surprising feature. What we find is that as alpha gets very small, there becomes the possibility that theta can approach any value. It's no longer bounded between this typical value of 0.5305 and about 0.5. So the reason for this variability has to do with the equation, the definition of theta. In the denominator of that equation, there is this ln alpha. As that value approaches 1, the equation blows up, provided that kappa A is not equal to kappa B. This typically occurs at low temperatures, but it can occur at fairly high temperatures, with low temperature being a relative term based on the system. However, we can re-reference these models using cap17. In this plot, in the plot to the right, the y-axis is now differences in cap17 between the two hypothetical species, and the hyperbolic relationship no longer exists at alpha equals 1, or in this case, the natural log of alpha equals 0. The majority of the variability exists within plus or minus 0.3 per mil for Earth surface conditions. So in the same way, we can also consider kinetic isotope effects, or KIEs. Under transition state theory, KIEs are characterized as resulting from a pre-equilibrium between a reactant and a transition state. The difference in this case is that a transition state is unlike a stable molecule in that it lacks one vibrational degree of freedom that's lost to the decomposition mode. This is called the imaginary frequency. So the contribution from the imaginary frequency is given by this ratio of frequencies here. This equation yields very different values from the equilibrium model. For instance, here on this plot is on the x-axis is beta for that model. So this is like an alpha value between whatever species you have in question and a monatomic oxygen. And on the y-axis is kappa. So unlike for stable states, kappa for transition states can vary. It can diverge in the same way that theta can. This really has to do with, so as a result of this kappa varying like this, theta values for kinetic isotope effects are more variable than for equilibrium isotope effects. So in summary of this section, equilibrium and kinetic isotope effects can be modeled using basic physical principles. Both equilibrium and kinetic theta values are unbounded, but they largely exist within a range of 0.5, really 0.52 to 0.5305. And kinetic isotope effects are more variable than equilibrium isotope effects, but I should note that they commonly yield lower values of theta. So what about real molecules? This is an infrared spectrum of water. Experimentally, infrared spectra are one of the ways that we can determine molecular vibrational frequencies. So here I'm going to focus on this red curve that gives the liquid spectra of water. Sorry, the spectra of liquid water. I model liquid water using a cluster approach. In this cluster, a group of water molecules is surrounded by a set of optimized but frozen water molecules. The reason for treating the boundary of the cluster this way is to try to, as best as I possibly can, for the interior waters, simulate the exterior system. So we can then compare the experimental spectra to predicted infrared absorption spectra. And what I found is what I think is actually a remarkably good match, considering that this model at this stage is just a harmonic model. There are, however, two features that are missing. So we largely reproduce this low frequency range with low wave numbers, as well as this peak here. But we're missing these peaks here at around 2100 and this broadening that occurs between about 1200 and 1500. So those can actually be generated if we start considering anharmonicity in the model. And so this model that I'm presenting here is actually a fully ab initio anharmonic liquid water model. And by incorporating this anharmonicity, I can then generate isotope fractionations that I believe are fairly accurate. And so this is actually where I've been getting the fractionations I've been showing for CO2 water so far. So that brings me to the final part of the study. We would like to model minerals using cluster methods, and which these methods allow for more accurate treatment of the wave function or the electron density, depending on what method you're using. The deficit, though, is that the model construction is not as good as something, say, with periodic boundary conditions, because we have to truncate the cluster. In these kinds of models, computer resources are always limited, so it becomes necessary to evaluate the accuracy of affordable models. We devised a test to evaluate affordable theoretical models for the calculation of isotope effects. We chose quartz as this test mineral because there are fractionation curves available in the literature, and it is a fairly geologically relevant mineral. The base model used for this test consists of all of the atoms within 5 bonds of a central silicon atom that's chosen from a published quartz structure. Bonds at the edge of the cluster are then truncated with hydrogens, which we can do in this case because they have a Pauling bond strength of 1. And then atoms within 4 bonds of the central atom are then allowed to freely optimize. The external atoms that are attached to the hydrogens, which in some cases are bridging silicons, in some cases are oxygens, those atoms are left frozen, and the internal atoms are allowed to freely move and vibrate. So to do these calculations, we've chosen to use density functional theory, and this is really for affordability. This is really in order to get accurate treatment of electrons as well as affordability. Density functional theory, specifically the Kohn-Sham formulation, has two major components: the functionals and the basis sets. So I'm going to begin with the functionals. The functionals have been described as existing on a Jacob's ladder of sorts. The bottom rung is the local density approximation. In this approximation, only the electron density is considered. The LDA can generate accurate geometries, but it's generally insufficient in most cases for many parameters. To advance past the local density approximation, the derivative or the gradient of the electron density is considered. And that's what yields these GGA functionals. Moving up one ladder, the same step is taken to now consider the second derivative of the gradient, which yields the meta GGA functionals. Another pathway to higher accuracy is the introduction of a portion of exact exchange from Hartree-Fock, which is what yields the hybrid functionals. The hybrid functionals are perhaps the most popular functionals. B3-lip and PBE0 are probably two of the most popular, with B3-lip being by far the most popular, whereas PBE0 operates well for liquid water generally. There are other things that can be considered. To move up one step, what's usually put above everything is the hybrid meta approach. That's a combination of the meta GGA, the second derivative approach, as well as the hybridization with Hartree-Fock. But there's also other things to consider, such as range separation when choosing a functional. As moving up the ladder, generally there's greater accuracy, but the expense of that accuracy at the expense of greater computational cost due to greater complexity. So the primary factor, though, is in determining the computational cost of basis set will be the primary factor in determining cost is the choice of basis set. So here I'll be restricting discussion to localized Gaussian basis sets. Basis sets are functions that describe the electronic wave function. So you can think of these like degrees of freedom for the electrons. Basis sets also, in a way, exist on a hierarchy, with the minimal basis sets considering the least degrees of freedom, in essence, with higher basis sets including more functions that describe the wave function. Required computational resources increase rapidly up this basis set ladder due to a typical end to the third scaling with both the size of the basis set and the number of electrons. So, for example, a quartz model that I showed earlier, if I was to pair the BLYP functional with the Popol 631G star basis set, that model takes about an hour and a half to run on my home workstation. But if I were to pair the PBE0 functional with the triple zeta AUG CC PVTZ functional, that takes greater than a week to run. So for this model, the computational efficiency parameter is decided on by using small basis sets, fairly small basis sets that are double zeta. So the basis sets we've chosen to use are the Popol 631G star or 631GD basis set, the Dunning CCPVDZ basis set, and the Kalrush Def2 SVP basis set. These three basis sets are paired with 8 different theories going all the way up the ladder from GGAs to meta GGAs, hybrids, and hybrid metas. 2 were selected from each rung of the ladder. So this yields a total of 24 different models that were run for this quartz cluster. So first we can look at some observable parameters. We'll start with the strongest infrared active frequency. The measurement of that is 1,171 wave numbers. Or inverse centimeters. That frequency contains a component of anharmonicity, which typically yields lower frequencies than the equivalent harmonic frequencies. What you can see from the model results is that most combinations overestimate this frequency, but again, the harmonic frequency may be slightly higher than the measured value. With the best prediction without scaling being the PBE and BLYP functionals. Those are both GGA functionals. Those are particularly accurate when they're combined with a CCPVDZ functional basis set. And this basis set also typically underpredicts relative to the other basis sets. Another thing we can look at is the silicon-oxygen bond length. This is essentially a measurement of the structure because quartz only contains silicon-oxygen bonds. The measured value is 1.608. That's what was in the structure that we started with. Most combinations overestimate this bond length. The best prediction is M11L, which is a meta GGA that it's similar to the M11 functional, but it removes the Hartree-Fock component. And that's particularly using the Popel and the Karush basis sets. The CCPVDZ basis set typically overestimates this bond length, and that could be correlated with the underestimation of frequency seen in the previous slide. So what we really want to look at is isotope fractionation, and we want to compare how accurate these models are, or how precise these models are really. And so what we can compare to is a previously published theoretical curve. This previously published theoretical curve comes from Hayles et al. 2018, which compares fairly well, although has a little bit difference in theta from experimental results from Zach Sharp's lab. So looking at these plots, the top series of plots is the difference in the delta 18 fractionation, or the difference in the natural log of alpha from the Hayles et al. 2018 model. And what you can see is that there is a good 10 per mil range in the values that are predicted by theory at 0 degrees Celsius. Now, this is a lot larger than we originally thought it was going to be. But if you were to look more carefully at these, you can see that the ones that are actually deviating down are the GGA functionals as well as revised TPSS. These would be the ones that would generally be predicted to be the least accurate. And the one that's predicting upward is the M11 functional. And that could be due to the way that functional's created by fitting to, I believe, by fitting to a series of observables rather than trying to reproduce the behavior of the electrons. The remaining cluster is actually fairly well focused within about 3 per mil of 0. Moving across the basis sets, CCPVDZ, you have similar agreement between the values, across theories, but CCPVDZ tends to underestimate the alpha values. DEF2 SVP compares very well with the Popel basis set, 631GD basis set. Looking at theta, it may look like there's quite a lot of spread here, but it's noteworthy that this isn't 10 to the minus 4. So everything that's varying in here is varying in the 4th decimal place. And so what this tells us is that even though we have a large spread in predicted values for alpha, we actually have fairly confined theta values. And so we can even use low levels of theory, very efficient levels of theory, to accurately predict theta values. So one way we could possibly make this affordable theory a little bit better is by considering scaling. One thing that should be considered is that the assumption in the equations that are used for isotope fractionation they assume harmonic frequencies. And so if you scale to anharmonic frequencies, it's conceptually inaccurate. And so what we've chosen to do here is to scale to some published scale factors, and these are scaled to CC SDT. This is a very high order wave function method. So these should be extremely accurate. This method is, however, far too costly to run on a model of this size. By scaling the frequencies to this function, what we get is a lot more accurate or a lot more precise values that are more accurate to the higher level theory. CCPVDZ still underpredicts pretty dramatically in alpha. DEF2 SVP still overpredicts slightly, but these are fairly good matches to the higher level theory. Theta becomes a lot more confined as well. So in summary, in at least some cases, harmonic frequency scaling to high level theory results in double zeta basis sets yielding kind of comparable results to triple zeta basis sets, at least for the atoms that we're looking at. I would expect that if you were start looking at larger atoms, transition metals, you would start wanting to use the triple zeta basis sets. The CCPVDZ models deviate strongly from the higher level triple zeta B3 lip models. So in my own personal work, I'd probably avoid using CCPVDZ, and I would probably use the triple zeta equivalent CCPVTZ, or maybe the Dunning or the Karush basis sets. So instead of reading through my conclusions, what I want to say is I think a fruitful direction for the field to move forward in is the study of kinetic isotope effects. Kinetic isotope effects depend on two things. One known, the reactant, and one unknown, the transition state. So adding the constraint of a second isotope gives us a degree of constraint on two separate aspects of the transition state. Using these separate aspects may make it possible to determine the transition state in a way that's not possible with only a single isotope effect. However, application of this idea requires marrying experiment and theory. So, okay, let's say thank you.
Yeah, thank you for your talk. So questions in the chat box?
No, we don't have any in the chat box.
Well, I'm sure people will ask questions about the kinetic isotope fractionation. So your limit is still 0.50?
Sorry?
Is limit 0.50 for kinetic?
No, kinetic isotope effects can deviate strongly above 0.5, below 0.50, as well as above 0.5305. That's not saying it'll happen in all cases, just in some cases it could.
Just thinking of Ed Young's paper.
Mm-hmm.
So feel free to send questions to Justin if you have, if you think of one. Yeah, thank you for presentation.